search trees. So to solve this problem, we need to know two concepts, BSTs and DP. BSTs are binary search trees. It's a tree where every parent has at most 2 children and the left child is less than the parent, the right child is greater than the parent. So in this case, right, 1 is less than 2, 3 is greater than 2, 3 is greater than 2, 2 to the left here has nothing, but it's still a binary search tree. It's just nothing right here. And that will come in, this will be important later on. DP right here is dynamic programming. It's all about solving complex problems with simpler subproblems. And we see this in action with the problem statement right here. We're given a unique integer n, and we want to find all possible BST configurations that are structurally unique. And we see this with n is equal to 3. Now, DP is all about solving it using simpler problems. What is the simplest problem? Well, that's when n is equal to 1. When n is equal to 1, you just have one node. So that's 1. When n is equal to 2, what are all total possible configurations of n is equal to 2? Well, we obviously know it's this or this. So the output is 2, the output is 1 for the previous case. But consider, how do we arrive at this result? Well, first of all, there's a little bit of math here. It's this scenario plus this scenario. So 1 plus 1 gives 2. Mutually independent cases, like these two configurations, are summed together to arrive at the total possible possibilities. So we have 1 plus 1. That's the OR relationship. But what about creating the individual cases, like this case? How do we create this tree from n is equal to 1? Well, consider the root node. When we consider the root node, it still is a binary tree. A binary tree has, let's just say for this case, it always must have 2 children. It must have 2 children. Except one children can be the empty child. In this case, this is the empty child. So the left BST, right, the left node has to be all BSTs with n is equal to 1. By the way, another property of BSTs is that, let's say this is a binary tree, right? This, the subtree that we can draw right here is still a BST. So by that property, this is a BST, and that BST is all BSTs with just one node. And this is all BSTs with 0 nodes. Or we can have all BSTs where the right child is all BSTs with 1 node, or the left child is n is equal to 0. And by convention, we set n is equal to 0 to be 1 by default. And the reason for this is because the number of configurations for the left subtree multiplied by the number of configurations for the right subtree gives us all total combinations of these two pairs. And by combining them, by multiplying them, we get all total combinations for one specific case. So that's the AND relationship, right? Because the overall tree of n is equal to 2 is dependent on the combinations for the left subtree and the combinations of the right subtree. So to create n is equal to 2, it's dependent on n is equal to 1 and n is equal to 0. So we multiply them together because they're not, we need them, those two are combinations of each other to arrive at all possible configurations to get to this output. So when n is equal to 1, we derived it previously, it's 1. Multiplied by n is equal to 0 to be 1, and we add that with 1 times 1, which gives 1 plus 1, which is 2, which is how we arrived at 2. And we extend this to n is equal to 3. So when n is equal to 3, consider the root node. Just consider the root, right? Consider the configuration of these two configurations, right? Consider just the root. So the first configuration looks like this. The next one looks like this. But regardless, what do we notice about this root? Well, the left child is both n is equal to 0. The right subtree, right, is always the case of n is equal to 2. And what about the middle case? This is where n is equal to 1, n is equal to 1 for this subtree and this subtree. And for the last and final case, we have the mirror image of the first one, where n is equal to 2, right? This is the n is equal to 2 case, and we have the empty child right here to be n is equal to 0. Same goes for here. N is equal to 2, and n is equal to 0. So basically what we see here is it goes from, for the left and the right subtrees, 0, 1, 2, 2, 1, 0. So that's where the DP comes in. We know that for n is equal to 2, there's 2 total possibilities. So forget this case. This case is included within this case, because when n is equal to 2, it accounts for both of the possibilities. It accounts for all possibilities where there's only 2 leaves or 2 nodes. Hence, it's just going to be n is equal to 0 multiplied by n is equal to 2 plus n is equal to 1 times n is equal to 1, right? Plus n is equal to 2 times n is equal to 0, where this right here is all the possible configurations for the left subtree, and this is the right subtree. So when n is equal to 0, it's 1 times 2 plus, when n is equal to 1 is 1, 1 times 1 plus 2 times 1, which is 2 plus 1 plus 2 to get 5, which is how we arrived at the 5 you see. So that's the DP. I hope you see the recursion here because we're going to program it up in code, and I hope it will become even more clear. So as we said, by default, n is equal to 0 is going to be 1. And when n is equal to 1, it's going to be 1. That's just by default. So we're going to store all this within trees, and it's going to be an array, so times n plus 1. This creates an array of length n plus 1, where the index represents the total configurations with a tree with n nodes. So when n is equal to 1 at index 1, it stores the configurations for all trees with just one node, and etc., etc. So with this, we can say for I in range of 2 to n plus 1, and we start at 2 because, again, we know what 0 and 1 is going to be. And for j in range of, or it's going to be, let's see, because it's going to start at 1, so 1 to I plus 1. So how did I arrive at these values? So this controls, right, n, right? It's going to be, okay, what about when there's 2 leaves, or 3 nodes, etc. This is going to dictate the number of children for the left and right subtrees respectively. So we're going to have a total local variable that's going to store all possible configurations for each possible combination at, there's I nodes in the tree. So they're going to have a left tree. The left tree is going to have how many nodes? Well, from the pattern we derived previously in the example, we know it's going to have I minus j nodes. The right subtree is going to have j minus 1 nodes. And the total at each iteration, each possible configuration for the left and right subtrees is going to be added to the number of possible arrangements for the left subtree, which is stored at trees of L, multiplied by the trees at the right subtree. And with that, we just simply trees of I is equal to total once this is all done, and we just return the trees of n at the very end to get the desired tree with n nodes. So that should be it. So let's run it. And it passes, so let's submit. And there we go. It solves everything.